Hello all, I'm Cale Kochenour, and this is the first video on what will hopefully be a series of videos helping you to build your geospatial talent stack. And so talent stack is adding together different skill sets that complement each other, and when added together kind of act as a force multiplier to make you more effective, more efficient. And specifically I'm gearing this towards a geospatial talent stack where I'm talking Python coding, Conda environments, automating routines, remote sensing, GIS, geospatial data, Earth data, anything along those lines to help you build your geospatial talent stack. And the first topic today is on open reproducible science, talking about project structure, how you can start off, what you can do to kind of better set yourself up for success by having a rigorous, organized project structure. We're going to start by looking at the GitHub repository that hosts the code for this project. The general premise of this project is within open reproducible science, it's generally a good idea to have a well-organized, rigorous project organization. And so I've got this structure here with 5 folders that I use basically for all my scientific and computational workflows. And so this specific repository provides some code to create this project structure within your environment. And you can certainly add some more granularity within each folder, which I do as well. But this specific repository provides the baseline. And there's 3 main parts. There's the Conda environment that you'll run your code in. There's the actual code to create the folders, and a makefile to help out with some automation and automating some routines. So I'm going to briefly hop into each of those files and then show a demo of what exactly you can do with it. First off is this environment.yml file, which you'll be using to create the Conda environment needed to run the code. First off, line 1 shows the name. You can name this anything you want as long as there's no spaces in the name. This one here is specifically titled Reproducible Science. Lines 2 through 4, the channels. These are the specific channels you'll be downloading packages from. And then lines 5 and 6 show these specific dependencies. In this case, it's a very baseline number of dependencies with just Python 3.9. In a larger project, you'll have a lot more packages depending on what specific tasks and processing you'll need to be doing. If I hop back out, actually get into this code, this create folders, create-folders.py, that will create the folders. The main content of this file, lines 23 through 34, will create the files within whatever your current working directory is, or create the folders within your current working directory and skip them if they already exist. And finally, jumping up to the makefile, one of the things as your projects grow in size and modularity and repetitiveness, and you really want to help wrangle them, one of the things you can do is introduce some automation tools. And makefiles are a way to create routines where you can run one or a couple keywords, and it runs a bunch of commands to help automate the routine. So specifically here, lines 5 and 6, I have this create routine, which is actually going to run the Python script for you. Not completely necessary for this because to run it in terminal, all you type is Python create folders.py. But so you're not simplifying too much, but then you have lines 9 through 14, which this clean routine, which deletes all the folders and the contents of the folders. And as your workflow grows, you'll have much more complex routines, and that's where it's really important to have these makefiles to really increase your efficiency and help automate. So let me jump back to the main GitHub. What I'm going to do is I'm going to launch Binder, which will open up the project online. So basically it creates an instantiation of the repository where you can access Jupyter Notebook and all the files and terminals to run things and mirror what you would do locally what you want to do. Generally, this takes a long time to load. The more you access it, the quicker it loads. I'm going to let it spin here, and then I'll see you on the other side. Looks like that didn't take too long, and we're back here. So you can see we're currently in Binder, which has a Jupyter instantiation up. And it's got all the files I described, as well as a couple other files that are in the GitHub repository. So what I also have, if I hop back to the GitHub repository, I have some instructions about what to do, how to run this, how to create the Conda environment, how to activate the Conda environment, and how to run the code. So first off is this creating the conda environment. So if I copy that, what I'm going to do is open up a terminal within this instantiation, and I'll paste in this conda env create. So what this is saying is, take the environment file we have created, we have in the GitHub repository, and create the conda environment based on all the information configurations within that file. So if I run this, generally this will take a minute, 30 seconds, 5 minutes, 10 minutes, depending on the complexity and number of dependencies you have in your environment. I'll just let this load, and I'll see you on the other side. And we're back here. So what you can see is the specific packages that were loaded, and at the very end it provides some instructions, which I also have in the GitHub repo. So let me clear the screen here, hop back. So we're in the terminal, so we just created the conda environment. Now we want to activate it. So conda activate, and then the name of the environment, in this case it's Reproducible Science. And what you can see here, before the terminal command in the top left, you've got this Reproducible Science in parentheses, which tells you which environment you're working in. One way to test which environments there are available to you, if you type in conda env list, it'll provide an output of which environments are available. These are the environments that are specifically in the Binder application. They've got a base environment and a notebook environment, as well as this Reproducible Science environment that we just created. And the one with the asterisk is the one that is currently active. Within your local instantiations, you might have a lot more, depending on what specific ones you've created. So if I hop back to the instructions about what we're doing, so now that we have the conda environment activated, we want to run some of these commands. And we've got down here in the run the code section, to run a command in a makefile, type make and then the name of the routine. So I have those two routines. One is create for creating the folders, and then one is clean for removing all the folders. So I'll run this make create and then make clean to demonstrate what exactly it does. So if I run this make create, some of the output just mentions that creates the 5 folders and the script is completed. To prove this worked, you hop back to the Jupyter instantiation, and now you've got these 5 folders. The difference, so within this Jupyter instantiation, this does not affect my GitHub repository at all, or if you clone or fork this repository, it will not affect your repository. It just creates it within this local Binder instantiation. If you did this locally, it would be different, and the folders might be more permanent, but when you close Binder, it closes everything out and exits like you've never started it up. Next, I will write the make clean command, which just removes all the folders. If I hop back to the Jupyter instantiation, all the folders have gone. Hop back to the terminal. So that's specifically what the code does here. If I jump back one file at a time to the GitHub repository, the remainder of the README just talks about what the files are for and then describes what the folders are for. And again, you can certainly create more granularity, add folders, take away folders. My general premise for this tutorial was to get some ideas out there about open reproducible science, creating a rigorous structure, and some automated ways to help you out with that and get started. I do want to thank you for watching. Hopefully you learned something throughout this tutorial. Again, my name is Cale Kochenour. Information in the description of how you can get a hold of me. As well, I wrote a complimentary Medium article that puts some of this video and instructions into text, and as well there's a link to the GitHub repository to access all the code. Thanks again.